scheduled. So that's what we're going for. Because that's before spring break. And I just think tests after spring break are a bear. Like if we study all this material, then go on a week's vacation where we all go brain dead, and then come back and you have to have a test. Spring break? I've got it on my calendar. Let's see. But I don't know if it coincides with Keokuk. Drum roll, please. It doesn't coincide with, yeah, there's all my stuff I'm supposed to be doing. Okay, March. Oh, April. No, come back here. Spring break, our spring break. Final answer. 11th? Starts 11th? Yep. When's it end? The 15th. So it's Monday through Friday. Yep. Monday through Friday, 11th. Be here before you know it. And actually, that, yeah, I hesitate to tell my classes this, but you guys can handle it. A week from Friday, there's no class. There is class this Friday, but a week from Friday, it's like teachers in service. So I'll remind you. Any other questions? Good stone, RJ. Just kidding. Okay. So cute little atoms. So here's where I get to tell you, and I'll just kind of jump ahead. Well, you kind of know a little bit about an atom, and I think we might have talked about how the atom has protons and neutrons and electrons, and it's kind of organized, but they didn't always know this. So this is a like through time sort of look at atoms. So Dalton actually, and he wasn't the first one, but he actually was the first one to put together a formal theory of atoms, Dalton's atomic theory. We're going to take a look at it. And he said that all matter is made up of cute little things called atoms. Notice that in this, the words kind of go along with the pictures. So if you look at the yellow picture, that's actually Thomson's model, and the difference between Dalton and Thomson is, of course, Dalton recognizes there are positive and negative pieces to an atom. But he thought it was, and it's called the plum pudding model, he thought that actually they were all dispersed, which now we know that the protons are in the center of the atom and the electrons are outside. Electron cloud. Then we have the purple one. So the purple one, that's Rutherford. And Rutherford went ahead and he organized, he identified the central nucleus where the protons reside, and kind of that hazy looking purple, that's the electron cloud. That's Rutherford. Now Bohr went ahead and he focused on the electrons. So the difference between Rutherford and Bohr, again, I'm just kind of looking at the pictures because they're pretty good, is that Bohr said that all electrons are not created equal. And they aren't. The electrons themselves organize into orbitals and subshells and principal energy levels. So that's what Bohr came up with. And then we get onto Schrodinger, and it kind of makes me itch. But the thing about Schrodinger, the difference between Bohr and Schrodinger, it's kind of a subtle difference. But these little black prick marks are kind of showing you where electron particles can be. And it's kind of I guess I don't have the link to kind of show you the video, but it uses, we're entering more quantum mechanics, like the slide says, and it's like a cloud. There's uncertainty in where an electron is, and that's kind of where Schrodinger comes in. Okay. So Dalton's atomic theory. I've got some, I don't know if you guys can, and I don't want to embarrass anybody, but if you can see color, maybe you can see two colors there. First part of the sentence is black, the second part of the sentence is blue. And the way this works, this slide works, is if it's blue, it's like part of his original, what Dalton said was original, but it's not quite right. Dalton said that all matter is made of atoms. Cool. He went on to say that you cannot destroy an atom. And we kind of talked briefly, especially some of the unstable atoms, they we kind of destroy, they kind of fall apart. Even. So it's possible, I get my fusion and fissions mixed up. That's type of what we call nuclear fission, breaking up an atom. So it's not quite right. I have another not quite right thing, but a lot of very much right. Another tenet or main point of Dalton's atomic theory is he said that atoms of the same element are identical in chemical properties. But he went on to say that all atoms of the same element have the same mass, and that's not true. Also, you guys know there's this thing, we'll talk more about it, but there's isotopes. He went on to say that atoms of different elements will have different masses and different chemical properties. Okay. So here we go. We know that compounds are formed by two or more elements that are joined together, and they're joined together in a set whole number. So like we can write formulas. So one of the things you already knew is water. We can write the formula of water as this, okay? Now the thing, it's kind of a subtle thing. He said that these subscripts, how they combine, you're going to have relatively small whole numbers. And I think the point here, why this is in blue is incorrect, is if you've ever studied like biology, you know that the molecules of life become very large, and so they're kind of large whole numbers. This one we have red here, and the red was actually been added to what he originally said to correct his statement. So it's true to say that atoms are neither created nor destroyed. If you add, it's kind of back to what we just talked about a minute ago. If you go ahead and add, say, you can't create or destroy an atom as long as the process you're talking about, the chemical reaction, is an ordinary chemical reaction. So to distinguish ordinary versus basically nuclear. Okay, so ordinary, you're set. You can't destroy it, you can't create it. You can just skip over here into other sort of chemical reactions, yes you can. Okay. So in this universe, there is a principle of conservation of a lot of things. There's conservation of angular momentum, conservation of energy, conservation of matter. So you should be able to track the matter. So atoms are neither created nor destroyed as long as you're talking about an ordinary physical chemical process. And all matter is made up of atoms. So I feel like this is like just saying it in a different way. So atoms aren't created or destroyed. Matter is not created or destroyed. We count on that when we do a lot of labs, okay? And mass is not created or destroyed. Makes sense. They're all kind of saying the same thing. These all have the same caveat that you're not talking about some sort of nuclear chemical reaction. It's an ordinary chemical reaction. All right, dun, dun, dun. Problem set. Well, I was getting ready for today's lecture. I'm like, man, there's a lot of little problem sets here and there. All right. So I feel like this is a little bit going back. This is kind of redundant. The previous slide, like after the Dalton, we had Thomson, and this is Thomson's called the plum pudding model, where actually they didn't know about the nucleus yet. They had the electrons and the protons kind of in with each other. This would be more than like Rutherford's model. Well, this is actually just maybe the model that we know today. If we look at the dark colored center, that's the nucleus. And in the nucleus, we're going to talk more about it in a minute, but we have protons and neutrons. And that kind of light colored, that's the electron cloud outside. And one of the things I'm going to try to convince you of is that electron clouds are not always kind of this pretty little spherical shape. Electron clouds kind of take on some things more interesting than this. I have BBs in the lab, so I forgot to bring my BBs, my munitions. But this says let's see, yeah. If you make a BB and you make that the nucleus, and go ahead, then you have to have your electron cloud around your nucleus. Okay, you would have to have put the BB the way I read this. You would have to go up to the 5th floor of a 10th floor building with your BB, and you'd be kind of between 5 floors up, 5 floors down. And that's kind of, relatively speaking, if size-wise, the way an atom is. So this is the nucleus, it's a BB, 5 stories up, 5 stories down. That's your electron cloud. Yeah, cool.
So would stories be like a definite way of measurement? Like,
No.
Is that like a standard? Not in like the science field, but in general, is there like a standard height for a story? Or
10 feet.
Yes.
Because, you know, rooms have different.
That's what I was thought.
Yeah. That's a good question. I don't know. Yeah. So, all right. So the 3 little pieces of an atom you need to know in here. And again, I think I might have mentioned in physics, they break these down further. We're just going to talk about the protons, the neutrons, and electrons. And you'll kind of see this symbol, this convention. So protons, the letter P, lowercase p, little plus for what's charged. Neutrons have 0 charge. That's why the little superscript for a neutron is a 0. Electrons have a negative charge, so lowercase p and superscript negative. It's kind of nice the way this works out, that the charge associated with a proton, positive, and electron, negative, they're actually the same magnitude of charge. It works out well. So this is kind of what we're talking about. We're talking about an atom. In the center, you see the 2 colors, and the 2 colors represent this one is color-coded. The red ones are the protons, and the blue ones are the neutrons. And they are in the nucleus. And so you already, based upon the whole BB and 5-story or 10-story building, you've got a sense for, we can't really depict an atom and an electron cloud on paper like it really is. But we can kind of show the electron cloud outside the nucleus. This one I have to so let's read the caption. So we're going to take a single pebble, like take a pebble. Okay, I know we can't take a pebble, but within that pebble, these are the atoms that are within that pebble. Okay, if we were to take every atom that's in the size of the pebble, okay, so then we're going to take these atoms and we're going to scale them up to the pebble. And so then you have scaled the atoms up to the size of the pebble the atoms are in. So basically from a pebble, from the atoms in a pebble, you're talking about the size of magnitude Mount Everest. It's just to kind of show you how little atoms are. So in a single pebble, there's lots of atoms. Scale those up the size of the pebble. Again, I kind of go back to how big is the story. You know, I mean, it's a very loose, but I'm sure it's been crunched out. Sometimes I'll take these and work them out myself. Okay. So, what do you need to know about the protons? Well, they're positively charged, found in the nucleus. Some of these things I feel like we've talked about. What else do you need to know about the protons? I think we kind of, let's go back next. Protons are what make the electrons want to be part of that atom, because unlike subtract, so you kind of have this positively charged nucleus, plus, 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 and that's why the negatives stay there. That's why the electrons come out. There's 3 particles you need to know. I said protons, neutrons, and electrons. And one of them is basically massless, the other 2 weigh something. So protons and neutrons, they have similar masses. You're going to see here in a minute. Nearly identical masses, and they are what gives the atom heft. Electrons are masses. So this last one, I kind of feel like we've already alluded to this, or kind of talked a little bit about this, that on a periodic table, for any given element, we can pick on iron. For any given element, you have the symbol, and you have the whole number. That whole number is what we call the atomic number, and that is the number of protons. So when I say on my slide, it defines the atom, defines the element, that's what I mean. So if I were just to say, I've got an atom here, and I don't know what it is, but it has 35 protons, what would it be?
Bromine?
They would be bromine, yep. And that's what I mean by protons define, yep. And I'm digressing, but I remember like the whole like alchemy, you know, I know that's like not a science, but the whole taking something like, let's see, let's find, you know, here we have silver and gold. So like, if you want to do alchemy, I don't know how to say it. So you take something like zirconium. So you basically got to go ahead and get 7 more protons in it to turn it into. Does that make sense? That might not be a good example, but alchemy is silly. But I just think about that, like, how much does that look like? And actually, what I kind of described is you can take 2 small atoms and push them together, and we call that fusion. So that's a nuclear fusion. And some you lose some mass at that point. But that would be probably what I would do if I was going to try to turn zinc into silver. But I won't do that. Anyway, it's not that simple, but it is kind of. All right, neutrons. Neutrons are N with a superscript 0 because they have no charge. So already kind of looking at your next unit exam, I'll have some questions about all these. Where are they located? Neutrons are found cozy in the nucleus with the protons. And so a minute ago, remember I said, does protons help keep the electrons in check? That whole charge, opposite charges, kind of make that electron want to be part of that atom. Well, the thing about the nucleus is if we just had a ball of protons in the nucleus, they might not want to coexist because they have this repulsion for each other. So when it talks about the glue, that's what it's talking about. In the nucleus, we have the kind of the fighting repulsion of the protons diluted by the presence of the neutrons. Right. So what what has some heft? Well, the protons have heft and the neutrons have heft. And what I mean by heft, I mean weight. Third subatomic particle, dun dun dun, the electron, negatively charged, found outside the nucleus. We'll be talking more about what the characteristics of how much energy electrons have, kind of the general shape of the electron cloud, but they're definitely found outside the nucleus, way outside the nucleus. And so, kind of again with the BD and the 10-story building, it's the electrons that actually give any atom its volume. When we talk about stars living their lives, and stars actually can come to a point where they've aged and they're kind of collapsing in on themselves. They can actually collapse to the point of creating a density, a critical density where, I'm trying to think neutron stars where electrons and protons combine to form neutrons. But anyway, electrons give the volume of an atom. So when we talk about, I'll just kind of do this. I had a H2 up here. There's my oxygen, hydrogen, and hydrogen. Of course, this is a water molecule. When we start to talk about, well, how do those 3 atoms get together? We're going to see actually it's the electrons that help make that happen. All right, this one doesn't animate, but if it could, it would just kind of show you see the 2 colors, kind of the green and the blue in the center, those be your protons and neutrons in the nucleus. And we have kind of the itchy sort of, those are your electrons. Animating would show the electrons moving. This is kind of a blown up version. All right, so 3 subatomic particles. Boy, yeah, those are very light masses. And I told you that the protons and the neutrons bring the heft, right? And I said that they are very similar. They're similar actually to 3 significant figures. in mass. So when we're talking about the mass of an atom, that's going to be problematic. So we actually introduced using kilograms, was what I meant. Using kilograms is going to be problematic. So we're going to introduce another way of talking about mass, or another mass unit, and it's called the atomic mass unit, or AMU. So this is another mass unit, especially for atoms. Atomic mass unit. And actually AMU is the old-timey way. So atomic mass units anymore, I'm pretty sure this is right. And I can't remember. I think Tro still does it old-timey, but like me. But if you see this just the letter U, that could be atomic mass units also. But you can see where the electron is what we call massless, generally speaking. And then the last column, we know about the charge. Protons, positively charged, electrons, have no charge. Sorry, protons, positively charged, neutrons, no charge, electrons, negative charge. We have these problems. Yeah, we better keep going. I want to stop, we gotta keep going. Okay, this is okay. This won't be too bad. This is where I'm gonna kind of complain a little bit. The symbols, part of my job is to kind of get you used to vernacular and how things are done. The symbol Z means atomic number. Here in a minute, we're gonna see that A means something else, but Z is atomic number. And actually, sometimes my Z's look like this, just to kind of distinguish them from 2's. Okay, so Z means atomic number. And we've already been talking about it. It's going to be atomic number. And actually, I think we ran into that in part 1. These whole numbers are the atomic numbers. These whole numbers are the number of protons. So the atomic number must be the number of protons, and you're totally right. That's it. That's totally it. And this is one of the things that Gabe brought up the other day, and I think he might even picked on number 82. So, like if we pick on lead, if it has 82 protons in its center, okay, if it wants to have no charge, this would be like 82 pluses. It needs to have 82 minuses. It needs to have 82 electrons. If it's going to be neutral, if it's going to be balanced charge-wise. Now, not all lead atoms are balanced, but if it's going to be balanced, that's what it's going to be. So what this says is the number of electrons will equal the number of protons if it's neutral. Neutral means balanced, no charge. And we're going to talk more about how not all atoms will form ions. Okay, all right. This is where I'm like, really? Did you have to see? The atomic number is Z. Okay. Mass number is A. Like, I'm getting an A. But it's not. Okay. Mass number. Now, if you think of what the word mass is in the context of what we just talked about, the 3 subatomic particles, only 2 of them have significant mass. And so that hopefully will help you with mass number. Mass number is an integer. It's a whole number. Mass number means that you have gone into the nucleus of an atom and counted protons and neutrons. That's mass number. It's not a fraction. And it's not the same thing as mass. Okay, mass number. Let's do an example right quick. Let's pick on, that's not a good one. Oh yeah. No. Okay. Let's pick on phosphorus. So if I was going to draw a phosphorus atom, I would go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So number of protons, 15. Kind of using its mass number. Okay. I'm going to draw 16 neutrons. 1, 2, 3, 4, 5, 6. These are my zeros. 7, 8, 9, 10. 16. See how that works? Okay. So mass number, so I would say A is equal to 31. What's Z equal to? Yep. Z is equal to 15. See how that works? I'm just a visual person. So let's remember what we're talking about. So atomic number of protons. It's unique for an element, right? So in other words, all atoms of the same element have the same atomic number. What is atomic number? The number of protons. Same atomic number. All phosphorus atoms would have 15 protons in the nucleus. Atoms of different elements will have different atomic numbers. Put another way. Well, let's contrast the atomic number with the mass number. Mass number, not unique. The reason is the number of neutrons can vary. I'm sorry. So this guy can vary. Now, I'm not saying that you're like, oh my gosh, it can be 16, it can be 23, it can be 51 neutrons in a phosphorus atom. No, Mother Nature doesn't work like that. But it can vary, and scientists know what sort of variation we have out there. So, that's how they have different mass numbers. So it looks like you have some more problems. So we have just a few minutes. I'm not going to go on, but, well, I guess, because I want to talk about isotopes. Yeah, let's go on. We've got 5 minutes. Sorry, guys. We can do this. Seems like it's been a long day. It's not having these early outs that's throwing me off. Let's see if we can kind of wrap things into a neater box than just leaving this. So this idea of varying the number of neutrons, and again, phosphorus might not be a good example. I'd have to kind of look at the data to see if phosphorus is an element that does that. But as it varies the number of neutrons, we get different isotopic forms of the same element. So what are isotopes? They're atoms of the same element that have different masses. How could they have different masses? Or different masses, different mass numbers. And the thing is, they are kind of like in neutrons to kind of Mother Nature's salt and pepper, kind of the season. That's why you have atoms of the same element with different masses, different mass numbers. So an isotope will have the same atomic number. I'll kind of write it on my slide. Remind yourself what atomic number is. The symbol for atomic number is Z, and that's the number of protons. But we'll have different mass numbers. The symbol for mass number is A, whatever, right? And mass number is the number of protons plus the number of neutrons. And this, my friends, is what varies. All right. So this slide kind of says, some atoms have only, it almost sounds like an oxymoronic phrase, one isotopic form. Like, well, by definition, an isotope is kind of a different form of an element. So one isotopic form seems like a dumb statement to me. But other elements will naturally occur in two or more isotopic forms. So for instance, look, I picked one that only has one isotopic form. So phosphorus, it's not going to have, naturally speaking, an assortment of neutrons in its nucleus. But this list of elements will have, generally speaking, two naturally occurring isotopic forms. Hydrogen is an important one. So there's regular hydrogen. There's something called deuterium, which actually is like a little heavier hydrogen, and there's actually something called tritium, which does not naturally occur. And this one can have will have three or more versions of the same element, same number of protons, but they'll differ in the number of neutrons they move in. Okay, well that's a good place to stop. I feel better about that. Okay, so that's it, and we'll see you on Friday. Finish up this part and go on to the next part.